Hi everyone, I just wanted to put together a quick video for you today going over the conservation of momentum scenarios. So hopefully you watched the other video with the astronaut talking about how conservation momentum works in space, but it works the same here on Earth. And there are three scenarios. Generally they're not exactly as we call them here, but for the sake of what we're doing, I split them up in these three kind of scenarios: elastic, inelastic, and then explosions or separations. And so I borrowed a couple Lego devices here from my son. I'm going to go full screen. So I have two Lego vehicles. And so there's three ways they can have a collision. So you have two vehicles that are apart. So this is object one, this is object two, or vice versa, depending on which way you're looking at it. And so then this one's coming and runs into this one and then goes, and this one travels on. Or they may carry on the way they're going. They may be both moving and this one hits that one. Whatever the case may be, initially they're apart, one and the other, and then they hit each other and they're still apart. But all of the momentum that this has, plus this one before, equals all the momentum that each of them have after. So that's an elastic collision because they bounce off each other. An inelastic collision would be similar. They're apart before, so the momentum of this one and the momentum of this one. And if they're going west, then they have negative momentum, but the total momentum has to be conserved in these scenarios. So if this one is moving and then it runs into this and they lock together, like an object would in a collision, where if you had a truck run into a car and the cars smash together with the truck, right? So they're apart and then they collide with each other and they lock together, right? And it could be this one's moving slowly and this one in the back of it. This one could be parked, whatever the case may be. But they lock together. So that's an inelastic collision because they don't bounce off each other. The third one is fairly straightforward, and it doesn't really apply with the trucks, but you can think of it as if they're locked together, and they usually use like spring-loaded carts or rifles. If you had someone on it, so let's just say I had the one object. If I had this one object with the missile launcher on the back of it, see if I can pry that off there. He's going to be mad at me. So if I have the one object going and then this explodes, then it separates into two pieces. So they're one combined mass with one velocity, right? And then they split into two velocities. So that would be the momentum. So the combined momentum is a certain amount. Whether it's stationary, if it's stationary, this has a momentum, that has a momentum, right? And one's a negative, one's a positive, cancel each other out. Or this has a momentum and then that explodes off the back of it. It doesn't really matter as long as you realize the conservation momentum is conserved the whole way. And this one would be your third type, your explosion or separation. So just formulas to this. The formulas, a lot of people say, is the hardest part to pick. But if you think about it, elastic collision, say the two objects were apart. Well, in this, the momentum of A and the momentum of B are separate. They're two different parts of the equation. And then after, and that little prime means after, the little apostrophe, we call it prime, so they're apart after. In an inelastic collision, they ran into each other, they were separate beforehand, and then they locked together, so now their mass is one combined mass and they moved off together. So remember, they were apart and they locked together, so now they're one object with one total mass moving with one velocity. And the third one was the explosion, and beforehand the missile launcher part and everything were together, so they have a total mass, that's the mass in the brackets, with one velocity, and then they separate into two different masses with two different velocities. So if you just think about the formula itself, again, one time, elastic, the momentum, each object is apart and then they're apart after, and inelastic, they're apart but then they're locked together, so their masses are combined in the brackets. And the explosion is the reverse of the inelastic. They're together beforehand, and they split apart. Watch out for your negatives. Otherwise, it's fairly straightforward. And just pick the formula that makes the most sense. Thanks.